tried.
Yeah,
I tried.
Thank you.
Don't touch the table.
Are you going to stand there the whole time?
You gotta keep an eye on it.
I'm Maddie, I'm part of this year's UNSW iGEM team, and I'd like to welcome you to our first ever Synthetic Biology Symposium. It should be a great event. We've got a couple of fantastic panelists here. We're going to have a discussion, so feel free, if you have any questions at any point, to put up your hand and get engaged with the ideas. It should be a good night. So I'd like to welcome our panelists. Firstly, we have Mike Mayfield. He's from the School of Biomolecular Sciences and Biotechnology faculty. We have Matthew Kearns from the School of Humanities and Languages. Mark Deleu from the Faculty of Law. And Lawrence Lee from the Lee Lab in the School of Medical Sciences. So to start off with, I thought I might just explain a little bit about what synthetic biology is, because I'm not sure if all of you here actually know what it's about. So basically, synthetic biology is this kind of emergent field of science that started off about, the term was first coined about 100 years ago, but it's really only taken off since like the 1970s. And the iGEM competition has actually been a big part of that. Now what synthetic biology aims to do is to kind of take engineering concepts, so ideas of logic and putting things into kind of bricks, and take that to biology, so that we can kind of try and create a system where biology works just as well as engineering has in the past. The iGEM team is actually something that was started by MIT in Boston, and it's become this huge competition. We have over 300 teams internationally now, and it's really kind of driven this idea of creativity and innovation in the field. So that's why UNSW has a team, and it was super successful last year, and hopefully will be super successful this year when we go over in 2 weeks. Yeah. So to start off with, I thought we might just kind of get our panelists to talk a little bit about who they are, what they do, and why they're interested in synthetic biology. So Mike, would you like to start?
Cool. My name is Mike Mayfield. I work in the School of Biotechnology, Biomolecular Sciences. I'm an environmental scientist with a major in microbiology. So I have a great love for all things microbial, obsessive sometimes, considered. And when I was younger, in my 20s, if something was really interesting, that was enough for me to get really engaged. As I get older, if it's interesting, that's good, but I need it to be more and more applied somehow. This urgency, as I approach latter stages of my life, to actually affect positive change. I'm actually going back to my roots and bright-eyed and bushy-tailed, I can change the world. The difference between being over 40 and being just over 20 is that I have much greater capacity to actually affect positive change. So a lot of our research is based around development of biotechnologies, like technologies for increasing biogas production as a fuel, and technologies for biologically remediating contaminated environments. So that's me in a nutshell. Synthetic biology, I don't really know if I do it, and I'm not really sure I understand the difference between synthetic biology and genetic engineering. There's some, but maybe I can explain that to you. It's the
And can you tell us a little bit about your company, Micronova?
I can tell you a little bit about that. 2012, actually I'll go a little bit further back. In 2005 I started working on the biological degradation of organochlorines, and I was attending conferences in the US where they had brought industry and academia together, and in North America, US and Canada, there's a thriving biological remediation market. And I was sort of sitting there enjoying the science, but also sitting back and thinking, why doesn't this happen in Australia? Why isn't there this thriving biological remediation market in Australia? And I think the main reason is our sort of mining and agriculture heritage. It's biodegradation, the academic expertise were missing. And the and companies that do sorts of things like molecular diagnostics to tell you if this particular bacteria are in a contaminated site, and the provision of cultures if you don't have enough of those bacteria to supply those bacteria. So all of those things were missing. So I sort of mulled that over in my head for about 5 years and started a company in 2012 that supplied all of those things. So as the academic expertise were developing in my research team, then an interface between our expertise and companies, because companies don't always want to become embroiled or entangled in research agreements with universities. They'd much rather be doing something that's familiar to them, which is asking people to quote for some work and receiving the quote, deciding that they were going to go ahead, and then having the work done and then being invoiced for and paying the invoice, which is a commercial transaction, which they're much more familiar with and much more willing to engage. So we kind of put a shop front on our expertise at the university. That's been really cool because you have that experience and the great thrill, which is now a bigger thrill to me than publishing and getting grants, of actually cleaning up contaminated sites. That's a really nice feeling. Yeah, I'll stop rambling.
Yeah, that was great. Matt, do you want to tell us a little bit about yourself?
Thank you. Yeah, so my name is Matthew Kearns. I live in Moore with the Brown Building as part of the School of Humanities and Languages.
Love get you up.
Maybe after it's time. I enjoy coming to meetings where there's cider. So I'm 14, making Bankstown. So I too have a major in environmental science, but and also law. But as part of my studies, I transitioned again to an area which I didn't understand, which was actually the arts. So I transitioned out of sort of what I thought I was going to do with my career, which was being an environmental scientist, and became a sociologist. And in particular, studied in the area of the sociology of science. So I'm particularly interested in the relationship between science and society, and the multiple manifestations that relationship takes, and have particularly focused much of my research work on, I guess, areas where that relationship is sort of uncomfortable across a range of dimensions. So that can be areas where science has become a focus of controversy. So I've done some work on, for example, things like nuclear power and GM crops and nanotechnology, but also where science is, I guess, kind of advancing, and we're kind of struggling for tools to make sense of those dynamics. And I guess synthetic biology might be one area that form. And the kind of challenge in my work is sort of around how do we think about and kind of make sense of science in its kind of formation, its kind of formative period. Because what we've tended to do in the social sciences is we've tended to sort of kind of in a sense let science get on with it, and we come along about a century later and think, oh, well, how do you make sense of the car? And let's really kind of investigate the car. And I'm not sure that's good enough. I think we can do things a bit better. But there's a real challenge there, which is, how do we, in a sense, make sense of technologies and areas of science before they've fully developed? So how do we anticipate? How do we, in a sense, bring what I call the side of sociological inquiry upstream, so into the laboratory? So there's a real tradition in the area that I work in actually placing social thinkers, sociologists, into laboratory contexts. So that's a methodology of research called lab ethnography. And so I guess I've done a little bit of that throughout my career, actually engaging sort of up close with lab-based science. And that's been a real kind of learning experience over the years, and I guess a kind of side of some experience in conversations.
Great. What about you, Mark?
I live in a law building because it was fitted on campus, but my background is mainly in philosophy and political sciences, and so I came to law to teach and do research in legal philosophy. Now, one of the main branches of legal philosophy is what you could call natural law thinking, which more or less says that the law reflects human nature in one way or the other. It reflects human nature as the fact that, law is a system to constrain perhaps human nature in its aggressive forms, or it is a system to actually enhance human nature in its desire to develop a good life, so as Aristotle would say. So natural law thinking has both from a religious perspective and a secular perspective been extremely influential. And because one of my other interests is philosophy of science and philosophy of biology, I saw a nice link to looking back at natural law theories and that particular notion of, or the link between law and nature, both human nature as nature, you could say, and looking at how biotechnology and the biosciences more or less reconfigure that particular relationship between law and nature by making nature a kind of, you could say, instrument to reinvent not just nature out there, but even our own nature. And thus, there's a huge tradition that runs from natural law thinking also to things like evolutionary jurisprudence, or behavioral sciences, or cognitive psychology, or the neurosciences. So I've set up like a new research platform called Initiative for Biolegalities, where we not just only look at synthetic biology, that's just one form, but also to neuroscience or genetic manipulation of animals and plants, all kind of different levels, you could say, where the link between biology and law gets reconfigured. If you think of a concept of parenthood, which legally simply determines that there are two persons, a man and a woman, who are a legal parent, then that no longer maps onto what you biologically could call a parent. You can now have 3, 4, even 5 different biological parents, whereas legally we still want that to be 2 parents. It has been recently changed in the UK. So I'm also really interested in how biotechnology or the biosciences destabilizes particular legal conceptualizations, and how then there are attempts to restabilize those conceptualizations. So there's a famous scientist that also mentioned those very well, Shela Yasanov at Harvard, who has coined the term the co-production of law and biology, of law and science. So it's not like here we have biology and here we have law, and the law lags behind here and the law needs to catch up, and then the law will grasp or conceptualize what the law has done. But there are social processes, political processes, moral processes, and scientific processes who all simultaneously, you could say, dance around each other and come up with new configurations of products or notions of new inventions that are then stabilized or destabilized. And so I'm in a certain way also interested in what Matthew is interested in, these kind of tensions. And I think the tensions are very interesting because they show us what we want from these technologies, what we can do with them, and where we say the border is. And sometimes we draw a line, and that line becomes a legal line, and sometimes it is an ethical line, or it's a political line, or it's just a line that we need, to circumvent in a way. And so these are really interesting processes where law and our self-understanding more or less are challenged mutually. And I'm very interested also from a moral and political and legal perspective in that particular challenge. And synthetic biology is, of course, one field where the challenge is pretty radical in many ways.
Fantastic. And to get back to kind of the hardcore science, would you like to tell us a little bit about yourself, Lauren?
Sure. I'm in the School of Medical Sciences, and I just moved there about a year ago now. So in the Lowy Cancer Building, which is a big green building across the hall there. So I'm still trying to find my feet, to be honest with you. I got lost on the way here. I went to Samuel it wasn't so much a thought of, is this, what's the implications of this in the future, or this is the direction, or this is the way I foresee my career going. It's literally I'm looking along and find interesting things within nature. There's so many of them that I kind of explore that. And every time I do that, it keeps opening up, and I keep finding things which are infinitely more rich in the world we live in. So that's kind of my modus operandi. Synthetic biology. So I guess we kind of have two uses for it. One of it is in the use of synthetic biology for discovery. So I think, and some of my, so I should also say that this is for an iGEM team. I've supervised several biomod teams, which is a slightly different thing. So iGEM is International Genetically Engineered Microorganisms. So it's very much about engineering the genes of a microorganism to use them for some kind of purpose, such as bioremediation. Biomod is biomolecular design, where it's kind of one scale smaller, and you're taking biological parts, often DNA, and rather than using DNA, which we all know as information carriers to influence an organism, we actually use it to build things. So we're building little sensors, we're building, at the moment, this little tiny trap. It's actually called a tiny trap, which is like a string-loaded trap. It's so small that it's got 40 nanometers. So it's about as much as your fingernail grows in a minute. That's how big it is. It's spring-loaded open, and the idea is that we can rationally build these things with DNA now, and it opens up a whole bunch of opportunities for technologies, right? So if you can build a cage, you can functionalize it whichever way you want. Cancer treatment, for example, we often hit you with a sledgehammer. We give you a lot of drugs, chemotherapy, you get very sick. If you can encapsulate it and target it to certain areas, you can, in principle, reduce your dose 10,000-fold. So the problem with this, though, and this idea has been around, is how you get your little drug to sit inside the box, and that's energetically very unfavorable. So this team has built basically the Venus flytrap. So it's a little box which is spring-loaded open, and as your little particle comes in, it springs shut, right? So I supervise these biomod teams, and this is the third one. Winton here is a biomod superstar from last year, Jim Jeptamon, which is involved in synthesizing a vaccine. So why I like synthetic biology, I think what it does, it gives us a fundamentally new approach for discovering the biological sciences. So we, as biologists, are not really engineers. There's a lot of derogatory comments about us because we're not engineers. Schrödinger said all science is either physics or stamp collecting, right? And you say that because physics is kind of a very old science where they had fundamental principles from which they could derive truths about the universe, right? And what we're doing as biologists is so complex, we're just kind of like making observations and writing them down, so it's kind of like stamp collecting. And it hasn't actually been possible because biological systems are so complex, we're trying to build them. And so for pretty much as long as biology has existed, we haven't tried to synthesize biology. And that's a very different perspective to say, I've taken a cell which is already built, I'm going to poke it in a product to try and understand how it works. Right? That's what we've done as biologists, this top-down approach. Synthetic biology offers a completely different approach. I'm not going to give you the cell, I'm going to give you all the parts. Now, if you really understand how that cell works, you should be able to build it. And so it gives you a really rigorous test and a different perspective of how biology works. So that's the way I use biology for discovery. One of the things we're trying to build is this sophisticated rotary motor. It exists in bacteria. It's been clocked, it's spinning at 100,000 revolutions per minute. It switches directions in just a millisecond, right? And it's really, really small. And the crazy thing about it, it's also this ultra-sensitive sensor. It can communicate over distance, over 10,000 different proteins. And it's actually built of all these little tiny particles which are quite literally brainless. They have no idea what this motor is, yet somehow you can chuck them all together and reshape it, and they build themselves into these sophisticated machines. How does that occur? And in fact, every single natural system in nature is synthesized in this way. There's no pairs of hands, there's no director to tell where things go. We are literally a bag of brainless molecules, and somehow you have some kind of wisdom. So by trying to synthesize it from the bottom up, we try to discover about this type of process. The other interest we have in synthetic biology is biology has kind of existed for 4 billion years. And so biology quietly has been developing a lot of technologies. In contrast, if you can compare that to us, man-made stuff. We really have only been developing technology, I think, for the last maybe 300 years since the Industrial Revolution, even less than that. So before that, probably a hammer now was a hammer. 400 years ago, a hammer was a hammer. 1,000 years ago, a hammer was a hammer. It wasn't until really the Industrial Revolution where we started to develop technology. It was pretty young. It's only a couple hundred years old, right? So that means nature has a 4 billion year head start on developing technologies. So within nature, there also exists a whole bunch of opportunities to develop new technologies, and a lot of lessons we can learn by the way nature does things. So the bacterial flagella motor is another example. It's also known as an ultra-sensitive sensor. If we can understand how this works, if we can build it, can you use the same principle to build a sensor for diagnostics, for example? So we also are interested in synthetic biology to try to harness nature's design secrets to developing technologies.
Great, thank you so much for that. That was super interesting hearing about your research. I think I might start off by kind of picking up on the idea which you had, you're a supervisor of BioMod. We're here today for iGEM. As I said before, iGEM's kind of really driven this field of synthetic biology in some way. And I wanted to ask you, kind of, what role do you see things like iGEM and BioMod playing in the field? And do you see them as important kind of drivers of how synthetic biology might go, or what's their value, I suppose?
Absolutely. Again, I don't tend to read into the future exactly what role they will play in the future, but I do see the emergence of BioMod and of iGEM as very much like a natural process. There are some parallels with the other panelists here. That these kind of things within our society, as well as the different natural systems, tend to emerge, and by their own light, they kind of have their own life, they kind of reproduce, and by doing that, people hear about it. Students who otherwise wouldn't have heard of synthetic biology will have heard of synthetic biology through iGEM and BioMod. It also offers a different perspective on science. I think it's very easy from a student's perspective to turn your head towards a corporate law because there's a lure of money and prestige in that. What you miss, I think, if you don't look the other direction towards science, and I think this is where research experience at iGEM and BioMod can offer undergraduate students, is that the science is fun. You're spending people pay, I often say that people pay a lot of money just to buy Sudoku puzzles and Tetris and things to solve puzzles. We do this for a living. You literally, every day you're solving a new puzzle. And in solving a new puzzle, with another analogy, you're kind of rowing your boat on this untapped ocean, kind of stumbling across beautiful islands. So I think there's a lot of fun to be had in scientific discovery. And iGEM and BioMod, even independently of synthetic biology, offer a new opportunity for maybe the next generation or a few of the top students to turn their heads and say, oh, this is also pretty cool as well. Exactly what role is it?
I was actually just going to ask, for instance, do commercial interests turn up to these things as well? Like, are they scouting?
At the competitions? Yes. So I've only been to BioMod. The first year I didn't go with my students, this year, like last year I did. And it's smaller than iGEM, and we were approached by, the first year our team won, and they were then approached by a company. It was absolutely the students, it had nothing to do with me. They were approached by a company who wanted to work with us and develop some software for designing these little nanostructures, such as these little cages. Nothing came of it, but they approached us again the next year and said they wanted to work with us again. But the practicalities didn't really work out at that stage. I was approached at the end of the first year by venture capitalists who it was a bizarre thing because the iGEM and BioMod competitions are a very short time frame. We had a very innovative idea which we took so far as you can within a short time frame, which maybe showed the possibility the concept could work. But that was all. Maybe showed the possibility the concept could work. It wasn't like we had anything concrete. And I had some venture capitalists called from the US and they said to me, have you been funded yet? And then I said, oh, who are you? What's this about? They said, your project. And I said, what project? They said, oh, it's all over Harvard. Because they just won the competition. They were eager about it. And I said, well, which project do you want to fund? They go, the one at Harvard. And I said, the sense right? So they could talk freely about my project anyway. I didn't completely make it. I had one already, which I work at the National Institute of Health as well, so we had one already. I said, well, let's just use this and edit it. But then it was bizarre because I ultimately didn't want to work with it because they clearly had no idea what we were doing and I didn't understand why they were listing us. I didn't know whether we would actually get agreed to anything. So yes, we have been approached, but I felt like I was kind of fumbling around in the dark and didn't know what I was meant to do.
Yeah, so I suppose kind of what Mike just picked up on, one of the big driving factors in any kind of emerging technology is, you know, commercial interests and the interests of big companies to make money. But one of the interesting things that kind of has come out of synthetic biology is this idea of biohackers. And so I suppose I want to ask, you know, what is this kind of this tension or this contrast between big companies and biohackers, and where could that possibly take the field of synthetic biology? Maybe Matt or Mark would like to start.
Well, I think my short answer to that would be that much like in the IT sector, big companies will employ lots of biohackers over the next 10 years. And they will see in biohacking a particular kind of, I don't think hacking is itself a problem for companies. They will see a particular kind of mode of doing research in the same way that I think you just articulated, and they'll see that as a kind of valuable kind of resource. And they'll see in a kind of biohacking community a kind of a future kind of a kind of employee cohort. In the same way that the IT sector brought up effectively the kind of Napster brigade in the late 90s.
The Richard Feynmans of the world and the Steve Jobs of the world, maybe not Steve Jobs, probably Bill Gates, they kind of grew up playing with radios. That was their kind of hacking. Is this any different to that? We're now just hacking with different tools. And I guess from that pool, does that come a whole bunch of new trends?
Yeah. So I mean, if what you mean by hacking is playing, which to some degree, I guess you already talked about, like is the kind of vocabulary we use to talk about science. I'm not sure that it's like categorically distinct from like industrial scale biotechnology. I think it's kind of like the vocabulary. I guess what I'm interested in is what does that terminology of hacking reveal, but also what does it kind of not reveal? So it's kind of in a sense we talk about playing with biology. That sounds kind of interesting and kind of fun, but there are like interesting kind of questions around the nature of life and the kind of societal dimensions of some of this work, which the nature of the idea that we're just playing doesn't seem to kind of get us to. And so I'm kind of got ambivalent feelings about the idea of hacking because I want a kind of more honest conversation. And I
because you know a little bit more, because you've had a little bit of success, you try something a bit bigger. And then because of that, you start just thinking about different ideas. And then one day, you have a big idea, something you go for. And then there's another step. Do you really have the initiative or the drive at that point to find something really difficult all the way through? That's how I can imagine the process.
I mean, but then again, you know, assumes that this process of curiosity, driven by curiosity, is neutral. And perhaps when small children do it, indeed is neutral. But, you know, when it is done by adults, let's say there's always a certain purpose, there's a particular context, there's a particular notion of what am I discovering, what for. If it's only to satisfy my curiosity, then there are still also consequences of satisfying that curiosity. I think other questions that are evoked by biohacking that are much more fundamental is the differentiation if, you know, all this data is indeed freely available, so it's a part of the commons, you could say, open source, open access project that everybody indeed does not need to hack into because it is, you know, freely available, or if indeed this should become part of a patented database that you need to be allowed into, or as a commercial firm, or as a university. And it's not just about protecting intellectual property, but also safety. I mean, here I can, you know, give you a small example. Just recently, I had a conversation with Ryan McIntyre, who is the head of the School of Public Health here at UNSW, and she made this remark that really stuck in my mind, where she said, nowadays you only need 2 chickens and an internet connection to produce your own artificial pandemic. And she took that was not a joke being funny at all for her. That was literally deadly serious. Because when indeed in your backyard, you know, with a little bit of chemistry knowledge, you can produce viruses that might go global, then we all know that there is a need for what you said for biosecurity. So she's actually setting up a global center for biosecurity and hoping that lots of money will be provided for that. But I'm just saying, like, biohacking indeed is not a neutral process. If it is done for a certain purpose, and just playing around might be just satisfying curiosity, which is fabulous. That's what I would really hope for. But there are also lots of other implications, and I think there we get also to the legal or the moral aspects of synthetic biology, which is a fabulous neurological field, but at the same moment, of course, lots and lots of questions that come up for food security, for, you know, what can be done if we indeed, you know, develop new artificial forms of life, and does our whole notion of biodiversity change if we create new forms of life that we set out in nature. We have just recently set out a new artificial modified salmon in nature that grows 3 times as fast as a natural salmon, and now it is still in a kind of protected area, but when it would jump out of that and mix with all the salmons in the world, we would have radically changed salmon. Now, of course, you can say naturally there are modifications of animals and nature going on over thousands of years. So we could say, okay, there's nothing new. Or do we say, actually, what we are doing is really something completely new? And so we must identify if what we are doing is just a form of curiosity, or if we are indeed re-engineering life, and what the consequences of it may be. Are these consequences all positive? We have better food production, we have healthier lives, etc. Or are these consequences also potential threats, real threats? And thus we need to keep it in the lab, or we need to patent it, or we need to have complete transparency, which would then say we need an open source database. And so we have to make these decisions in the coming years to know how to handle this curiosity.
Yeah, I suppose I kind of want to ask, like you say, we need to kind of preemptively make these decisions in the coming years, but along with that, I mean, I know the view of one of our supervisors for iGEM, Daniel. He's very, you know, biology doesn't work a lot of the time, it's very difficult. I suppose I would like to ask Lawrence and Mike, do you think that it's very feasible, this idea of there being biohackers able to make a big difference in their backyards?
So it's actually, I don't know, has anyone read the book, Pilgrim? No, it's fantastic, it's a very chunky book, but that's the plot line in the Pilgrim. And there was one by, that's actually a Tom Cruise film.
every like 6 months or so, and that has been true since 20 years. Then if you would apply the same to microbiology, then perhaps might not be too far off. I mean, there are things that we can already do, like clone animals and humans, but they are just regulated that we don't want to clone human beings, for example. So technically, that's no problem. Even very difficult, but we have at least said that's not what we want. So I think the idea is not like any of you can either back garage and 2 chickens create it, but that potentially that will be the future.
So there's an interesting parallel. What you're talking about is exponential growth in the semiconductor industry.
Yes.
So that's what Moore's law predicted, that the speed of transistors will double each year and the price will halve every fixed amount of time. So you get this exponential growth. There was a fundamental reason behind that, though, and that's because of miniaturization. The smaller you get, things get fundamentally faster and cheaper. It doesn't apply to everything. So it doesn't apply to air travel, for example. If air travel was to develop the same way as transistors would be flying around the world for $20 and the plane would be the size of a shoebox. It doesn't. Certain things that don't.
But for example, it does apply to DNA analysis. To analyze the human genome took a decade. Yeah, took a decade. And now you can send in your DNA somewhere for $2,000 or $3,000. You will get your entire DNA analyzed. So in that sense, it applies to them.
Turns out who knows what DNA polymerase is. How quickly does that sequence your DNA? It's going to be a couple of hours in every cell of every cell of every body. You've got this DNA polymerase.
So there is a kind of nuance, which is, like Moore's law is presented as a kind of natural fact.
Yes.
But the Human Genome Project was a state-funded research effort. It was highly orchestrated.
Yes.
And like so you mentioned, so we've only been developing technologies 300 years. I'm not sure about that, but we've only been publicly funding technology development for the last half century, right? At least since the Second World War, since the Manhattan Project. So like before that science, what didn't have the hand of public patronage, right? In the same way that we do now. Like we spend a lot of money on science. That's probably that's a kind of good thing, right? But we need to be kind of honest about what that's doing. Do you know what I mean? So Moore's law doesn't exist as a kind of state of nature. It exists because we fund research that propels miniaturization. And so it's a kind of self-fulfilling kind of prophecy in a way, right? Because we tell ourselves Moore's law is essential for the continual growth of the semiconductor industry and thereby the kind of IT industry. And thereby we, in a sense, devote a huge amount of public funding to making that promise come true. And it seems to me that's very similar to what's happening in synthetic biology, right? Synthetic biology is making a kind of claim of the world. So a lot of the early kind of policy articulation of synthetic biology was synthetic biology will become the next industrial revolution. It will take over from the from the kind of IT kind of boom, the kind of next big thing. Now, interestingly enough, lots of other technologies have made those same claims, and it hasn't kind of worked. The biotech and Green Revolution made the same claim, and then nanotechnology made the same kind of claim. And this is a kind of familiar pattern. So folks in my field talk about the kind of what we see often, which is the sort of false humility of the scientific enterprise. So on the one hand, science wants to say, look, this is fantastic. You should fund this work. It's going to be the next great kind of discovery. On the other hand, they very quickly turn around and say, well, this is just curiosity. We're just playing around. We're just driven by the serendipitous kind of process of the scientific enterprise. And that's a fundamentally dishonest approach.
I think there's a little bit of complexity. I don't think it is that black and white. There is a bit of a dichotomy because of people who are allocated the funds and politicians who they need that story, right? And the reality is when you're actually on the ground doing research, there are a lot of different possible outcomes.
science is wonderful and great and all the rest of it. But on the other hand, we always say, but it's just serendipitous. It's contingent and provisional, and so we can't.
There's scientists playing to different audiences.
Yeah, quite. And so I think we can do better than that. Right? As a society, we can do much better than that. And actually, it makes science. I think it makes it more relevant, but also it also, in a sense, gives science credit for what it's actually doing. You know what I mean? To say there is a context in which science is being enacted. Those are meaningful. That makes science meaningful, but also makes it an object of kind of debate and kind of deliberation and sort of argument. We should have those arguments, right?
I think, just to add something to that one of the problems is that society itself has also not completely decided what it wants science to be. Does it want science to be fundamental, and does it indeed have to do with this curiosity, or does science always need to be utilitarian, namely that we can apply, that we can make money with it, that it doesn't cost us anything, that it will, pay itself back, etc. So do we all, or does it need to be, only for the things that will save humanity? Shall all research be directed towards cancer research? Or do we also have any interest in things that don't have a direct application or direct utility? And it seems that society can't really decide. We want it all at the same moment, but we don't want to give it all the same amount of money. So we actually want it to be all cancer research, because that's it's obviously urgent, but we also want the other things. But then you should just find some funding somewhere else, because we want you to do it, but we don't want to pay for it, because we can't sell this to the rest of the population that their tax money is going to. Some people are just looking at the stars all the time, unless you're planning a mission to Mars. And make a film.
That's an interesting point. So if you're interested in combating chronic illness, you would fund public health. If you're interested in bioremediation, you would fund environmental regulation. You wouldn't necessarily need to fund, biotechnological responses to cancer. We know that our improvements in health have largely been due to improvements in public health. So there is a cost. There is an opportunity cost here, right?
I like your wastewater treatment.
Sanitation, all those sort of classic things we kind of forget about. You look at medical research. The lion's share of medical research is not for things we know actually work. Now there is opportunity cost for the way in which we kind of think about and talk about science, right? And as much as we want to fund synthetic biology, it means other things aren't going to be funded. Now that's a big debate, right? And we should have that debate.
I don't think that is correct. You would to look for, if you wanted to cure cancer and you only find cancer research, miss the way to get there.
Yeah.
So if you wanted to, if you wanted to bomb the Russian with an atom bomb, and you are only funding, the development of rockets, particle physics wouldn't exist. I think the paths to any particular possible outcome are infinite. And it's very difficult to sit at the present and predict exactly what path is going to take us to a particular outcome. So I think the difficulty I'm having with trying to make the debate as you are is that we're trying to talk about something which isn't actually concrete. We don't know how to get there. We can't say, this is good because it's going to get us this, and this is not good because it's going to get us that. The truth is, I think, in discovery, what we do is we discover things. Curiosity, or because you're trying to do something in particular. And what happens is a general level of knowledge in the world goes from here to there. And often somewhere out of something we cannot predict, there comes a cure for cancer. It could come from a particle physicist. So
But to be sorry to intervene, but I think what Mitchell is focusing on is
what we do in reality.
Well, I don't know.
Spend more money on that.
But we put much more money on one box than the other, which is the kind of point, right? So we really stack the race. On
Which side?
So one way of thinking about cancer would be, how about we work on reducing people's exposure to, the kind of chemical, the array of chemicals that make it available in the world.
Are you saying we stack towards the public health side?
No, we stack towards the biomedical side.
Disagree. How much money's gone into shutting down smoking?
Okay, well that.
That's a big exception.
Right. Taking lead out of petrol, how much money's gone into fixing the ozone layer? How much money's gone into doing? I think most of it's on that side rather than. I'm not seeing that money.
Anyway.
In your research, Michael, I don't know, do you see a lot more money going towards people trying to fix up environmental pollution in ways that aren't, the best way with microorganisms, or do you get a lot of work out of that?
I'm sure I understand the question.
I suppose, do you think in Australia we kind of put more money towards, more classical ideas of how to fix pollution rather than, investing in, bioaugmentation, things like that?
No, I don't think there's been nearly enough money being given to me to do something. That's the obvious answer, but there's been a lot of money gone into developing engineering solutions, but that's generally not public money. That's private money going into finding an engineering solution for a waste or a contamination issue. I think relatively little of it actually trickles through academia to try and find solutions to these problems.
Well, I suppose we'll kind of move away from the idea of how money gets spent, things like that, and kind of to discuss the ideas of when we try to bring these new technologies into society and actually implement them in a real world way. Are there any barriers apart from the research which exist or which you've experienced in your kind of trying to implement a biotechnology?
Yeah. So I guess in my intro I touched on this a little bit. There are a lot of things missing in Australia. So I started a company that was selling stuff that nobody wanted to buy. And that's a pretty stupid thing to do, or brave, courageous thing to do. But I was doing other stuff alongside it. So I was talking to government regulators, I was talking to community groups, I was talking to industry, I was talking to academia, I was talking to whoever I could find that would listen to say that this works and we should be making better use of it because it saves money and it uses less energy and it's less intrusive and it's kind of a complete natural solution compared to digging aquifers up and bringing through catalytic oxidation and steam stripping equipment. I kind of realized that I wasn't just turning up with a shop front in an existing market, that I was creating a market, that had to be built as well. And I think for anyone interested in really commercializing stuff, I think you can have a great concept, a great idea, but you don't have something to sell. You go out and you get public backers and people to buy shares in your company, and you get a big load of money to try and build that thing that you're going to sell. I don't think that's the best model, so I haven't seen that be as successful as what more traditional businessmen do. And I think what I've been doing is pretty traditional, is actually just building it piece by piece and not rushing it, just, I'm kind of lucky that I've got another job because it wouldn't pay my salary. But I think that's kind of a very pragmatic way of doing it. You've got to look at what the obstacles are, but then have them in your peripheral vision, focus on the gaps between the obstacles, so you can keep moving forward.
Do you think that scientific communication was a big issue, was trying to get that off the ground?
Yeah, that's always a big issue. You've got to be able to explain it to your mother. That's been key, actually, to getting this idea into play within the industry, being able to sit down over lunch and maybe a glass of wine and just explain it in plain terms about all the science in really quite simple terms and everything. I kind of do science intuitively, and everything is related by analogy. That's how my brain works, which gives me this ability to explain phenomena to almost anyone but a scientist. Go, oh, look at that Lego. It goes like this. They go, oh, yeah, I get Lego. That's cool. Rather than baffling people with taking language. It's hugely important.
Matt, do you have any kind of ideas on, is scientific communication one of the major issues when it comes to implementing technologies, or are there other factors at play?
Yeah, so I guess this is an area I've looked at in quite some depth, because we invest quite a lot in science communication, and science communication is sort of, it's a bit of a hot button issue at the moment. So whenever there seems to be a kind of, a sense that things aren't quite going to plan, in any area of science where there's a kind of hint of, say, public concern, we often say, oh, well, we need to communicate the science a bit better to certain folks understand what's going on. And so there's a kind of sense there, so in terms of barriers, it's often thought that the general public are a kind of barrier. We need to get the general public on the side in order to kind of make sure that the process is successful. And so that's been at the heart of a lot of efforts to do science communication across a whole range of sort of contexts. And most of that stuff's kind of good stuff, right? We should be communicating our science, and we should be doing that in ways that are relevant and thoughtful and the rest of it. But there's a kind of assumption underneath that, which is, I think, worth examining. And it's what myself and lots of other people in my field call a deficit model. So it's the idea that publics have a deficient understanding of science, and that deficient understanding, or that ignorance, is at the heart of what they might be concerned about, particularly in novel areas of science. And so there's a lot of work on this around the kind of really substantial controversy over genetically modified crops. And it was an assumption that when you went into the research, you found was actually quite problematic, because the kind of concerns that people were expressing, or the concerns that people do express around lots of areas of science, are often because they actually understand some parts of the science. And it's not simply a question of their technical ignorance, but it's actually a kind of sense of, well, there's a set of concerns here that aren't being taken seriously by regulators, or by the government, or by corporations, and we feel these are relevant concerns. And more to the point, when we regulate technologies, we tend to only regulate technologies if they're kind of risky, like if they're going to kill you. So we don't really have a system of really thinking about the broader dimensions of what technology might be. So I've done a lot of work on this, in areas of science where that become the kind of focal point of public controversies. And in each controversy, what you find, and it's a very interesting kind of pattern, is you find a regulatory system that's really unable to deal with the depth of public concern. You've got this kind of sense that, if we just communicate better, publics will sort of come on board and be much more happy. And then a real breakdown in that system where you get all this sort of science communication work that's kind of good, right? But somehow it doesn't kind of really answer those concerns. And actually, what you often find is that becomes itself, it kind of inflames the controversy. This is a classic case of what happened in GM food controversy, particularly in Europe. And it's been a range of different examples on that front. So communication is great, but we need also to kind of invest in a kind of slightly broader way of talking about science.
So some of these concerns with things like ownership and regulation.
Yeah, right. So classic things like, who owns technology? Who's going to benefit from it? What's going to happen if things go wrong? Who's going to take responsibility? All these sorts of broader kind of social, political, and economic considerations. Is this a good thing to be doing? All that kind of stuff. What was really going on in the GM food controversy? What's happening? Lots of controversies about science. But we don't really have a system for. We don't really have a way of considering those issues in a thorough way. So our regulatory system designed to look at particular kind of technological artifacts and whether they're kind of toxic or whether they're risky or whatever. They're not, our regulatory system isn't really designed to consider, is this a good idea? How do you think about ownership? Is that relevant for us to be thinking about?
I suppose like linking into this, next idea of ethics and morals, where should synthetic biology be going? I suppose one of the things that CRISPR-Cas9 and those technologies have allowed us to do is to be able to edit the genome of almost any organism. Do you think that there are certain ethical and moral guidelines that should be in place or we should be thinking about when it comes to things like that?
It's a huge question, of course. I mean, always when there are completely new forms of, in this case, life. I mean, and we also have seen that in debates about abortion or reproduction or surrogacy, pregnancy, all these areas where it's really about life are always highly contested. And the question is always, when is it a moral problem or is it a legal problem? And I mean, also in justification to what you said, law is often seen as where this question is decided. At least some people would just say, if it's legal, it's all fine. Whereas other people say, wait a minute, there can still be a moral problem or political problem. But then, people who are concerned about the property claims or if they are allowed to do something in the land or not, will just say, well, legally, it's absolutely fine what I do. And so when the legal thing is settled before the moral and political thing is settled, then you have this classical notion of the clash, you could say. Now, I think in synthetic biology, we come back to this problem that the biggest part of the population has no clue what you are talking about and what the real implications of it are. So it's just a kind of imaginary idea that we can rewrite life and reinvent or re-engineer it, and that just brings up the Dracula and the Frankenstein ideas, and I mean the Frankenstein idea, and so it will just trigger a kind of fear perhaps. And if that is not channeled in a kind of transparent open debate about what might be the benefits and the risks, then it might go into the same kind of endless discussion as it was with the GMOs, and that will now be about the modified salmons and things like that swimming around in the seas. So I think it's the notion of innovation itself is not the problem. The problem is like what triggers this particular innovation. Does it trigger the sense of risk, or does it trigger the idea of benefit, or does it trigger the idea, there's some kind of private company like Monsanto who has now copyright on all soy production in the world, and so they will decide that all soy that we eat and drink will be modified, and we have no control over it. All those small farmers are going bankrupt because they can no longer afford to buy the product, etc. So there's a kind of secrecy within what's happening there. But it's legally covered by intellectual property laws, and so we can't do anything against it. And so I think another interesting, perhaps even more interesting question that synthetic biology triggers, particularly in relation to the law, is this idea that it seems to be clearly defined what can be patented and not by having the definition that something needs to be invented. Yeah? So when something is raw nature, we just had this big case of Marriott versus Darcy, which was related to if human DNA can be patented because a company knows to extract a particular cancer mutation that is linked to this particular gene DNA. So the question of property there is then linked to how do we define what constitutes an invention, and that always seemed to be very clear cut. Now synthetic biology more or less changes that particular definition because you no longer have anything like raw nature on top of which there's an invention. Like you no longer have just a mouse in the lab on which we grow an ear. Yeah? And now the question is that mouse still nature, 99% a real natural mouse, or is that mouse a product because we have put a gene in that grows that ear? And so this discussion, what is an invention and what is raw nature, has through synthetic biology, through that innovation, really gotten upon a new level, you could say, a new level of the discussion. And I think there is then the question, so when does the law step in, or do we just need a form of soft regulation of protocols and good conduct, or do we need a very hard kind of law that says the human DNA cannot be patented, or you cannot clone human beings, or you cannot by which we, can regulate it. We can say this belongs to you, or this belongs to all of us. This is part of the public good and needs to be protected, and that risk needs to be contained. Or indeed, we can let you fiddle around in your lab, and that's all fine, and we hope for good outcomes. So I think it is very complex, because it is indeed partly that the public doesn't know, and it's partly that there are so many new complex things going on that really changes our legal concepts that used to be able to control those processes by knowing what is an invention, what can be patented or not, etc.
So can I give you two guarantees? These are ironclad guarantees, and you take them to the bank. So the first guarantee is wherever we draw the line ethically, we will move. That will not last. So the ethical line between the living and the non-living won't survive. So that's the first guarantee. The second guarantee is we will then always struggle to define our ethics, and that struggle will then erupt in particular places as sort of social disruptions, as controversy. So one of the most fundamental moral categories throughout human history has been the distinction between the living and the non-living, the living and the dead, or the human and the non-human, or the animate and inanimate. But intriguingly enough, that definition has been changing, like over the course of recorded human history, and it is changing kind of again. Now we always draw the line, and then the line changes. We know that, right? So that's what will happen with synthetic biology. Synthetic biology promises to create a kind of artificial life, to recreate life itself. So we will draw a kind of ethical boundary around synthetic biology that will kind of prove to be kind of insufficient to the task, right? And that's kind of what will probably happen. And then that insufficiency will then create the conditions for a public conversation. Take those two guarantees to the bank. If you're a venture capitalist, you can kind of make money on it. As long as you can get a cut.
I suppose I'm just going to kind of note the time. I think I just want to ask one last question to our scientists here today, kind of about this whole idea of synthetic biology. We're trying to, apply engineering principles and be able to predict entirely, outcomes of biological organisms. Do you think that this is going to be successful? Do you think we can actually do this with biology?
Yes and no.
Like 999 no's and one yes.
So is the question, is there any particular example where we think it's possible at all, or we think it's
The whole item is that we can have this bio bank, and we can pick what genes we want to make an organism like that. Do you think that we'll ever actually get to that stage, or is biology too kind of complex that we have this wildness about it that we can't quite get there yet?
No, but we are getting there. People are engineering microorganisms to do certain things. They're engineering crops for a long time to grow in certain ways. So it depends on what your end point is. I don't think the idea of being able to have biobricks is fundamentally flawed. I think that there is a lot of use for that. Can we get there? I think we're there. I think we can do things already with biobricks. We can do things by engineering nature. We can do things with synthetic biology. But maybe there's another line of words, right? Could we make a synthetic chicken? Yes, we can. Or can we do this now? So I guess I'm not really sure where we draw that line. So I guess my answer is yes.
What about from your perspective, Mike, working on the larger scale of the microbes and things?
Yeah, I think a lot of it's going to work, a lot of it's not going to work, and we're not really going to understand what it is that don't work. I think that's the nature of science, and we are dealing with really complex systems, and as clever as we're getting, I don't think we kind of embrace that complexity yet, or be entirely comfortable with it. It's not completely predictable at this stage. But there's no reason why it can't become so, especially coming online now with machine learning and artificial intelligence and stuff. So that might go faster. But at the end of the day, you're manipulating these systems with little bits of plastic in your hands, and machines can do manipulations as well. But
these are kind of, there's an implied set of social, economic and political drivers that are really at the heart of that research enterprise. In the same way that curing deafness implies that deafness is somehow a deficiency that needs to be cured. That's for some people, not all, for some people, is a real problem, right? So what the argument is that there are right at the heart of lots of areas, in fact most areas of science, kind of implied social goods that often go really unexamined.
And just like you can become responsible for curing your own deafness because you could, you can become responsible for curing all kinds of other things. You have to diagnose yourself, let yourself be diagnosed, and then we can just rebuild your body more or less. And if you don't do it, you are actually not a good citizen because we expect you to be a healthy citizen. I mean, so the notion of biological citizenship, etc. We turn ourselves into biological citizens that need to take care of our own biologies. And so if it's possible to repair ourselves, let ourselves be repaired even on the micro level, then we ought to do it. So in that sense, the technology, the advance of technology, of course, triggers also a particular responsibility that applies to ourselves. And that's part of the whole narrative.
But to answer your actual question, which is can you do this in synthetic biology? Well, you guys have got the t-shirts, so like it's real, right?
Yeah. I suppose at this point I might just open the floor if anyone has any particular questions that they'd like to ask before we wrap up. Yes.
Hi. So is there going to be an intersection between quantum computing and synthetic biology?
I'm not a physicist. Quantum computing, one of the issues, as I understand, is quantum coherence. So you have a particle or some kind of thing which holds a certain quantum state,
Yep.
and it's called quantum coherence. But as soon as that interacts with something which is slightly big or anything at all, really, you lose that quantum coherence. So quantum computing at the moment requires, as far as I understand, a massive fridge, something or freezer, something which keeps everything down at 0 Kelvin. So it's not very practical. But then there's these little proteins in biology that exist in algae, which apparently can hold quantum coherence in water, in an algae in the sun. So who knows, nature maybe has solved this problem already for us.
Yeah, I was just going to ask Lawrence, there must be loads of examples actually in biology of quantum coherence.
Yes, there appears to be, but they're so difficult to measure. So they blast it with a whole bunch of microwaves, I think, and strong magnets. And you see a slight shift in the way the radiation decays. That tells you that this is quantum. So you get a squiggly line which looks like this rather than that, and that gives evidence that the biology is called quantum coherence. How you would then go and harness that, maybe I don't know. I guess in principle it's possible. In principle, according to that experiment, nature has solved that problem. And the real question is, are we going to be able to harness that solution for our practical purposes?
Next year's item project. Please.
About me.
Yeah.
Sorry, this question's for Nat. Obviously you deal a lot with the hostility, or you study the hostility that the general public has towards science and this kind of fear, and that's a huge thing in synthetic biology. Do you think it's possible to kind of have a society where this kind of hostility and this fear of something completely unknown doesn't exist, or do you think that's like a fundamental aspect of humanity?
They can genetically engineer it out.
What's your opinion?
So I would say we have one. So we don't live in a society that's fearful of science, and we don't have a general kind of anti-science or anti-innovation or a fear of the new, like, as we commonly represent it. The concerns as they do exist are often quite specific, right? They're often quite located. So like one of the things that occupies a lot of my research is in the kind of examples that you would imagine that there would be much greater public outrage are often the ones that are like really highly supported. stem cell research would be a classic case in point. And where the organisations that have tried to kind of, really activate on stem cell research, like religious organisations particularly, have been spectacularly unsuccessful, actually. So, the kind of areas where you would expect, oh, this is going to be amazing kind of, public controversy, actually, often in cases, are really kind of quite unremarkable. So I think the public conversation around science is often quite enthusiastic. But what I characterise it as a kind of public have a kind of ambivalent attitude towards science. So they hold contradictory understanding. So on the one hand, there's a kind of enthusiasm, but on the other hand, there's a sense that science advances, but also science brings with it, the kind of underside, the sort of underbelly of science. There's, industrial pollution. It's the hole in the ozone layer. It's climate change. I mean, this is the reality of modernity, right? These are the things that modernity has also brought, in as much as it's also brought, fabulous kind of life-extending kind of technologies.
The amazing thing is we don't get blamed for any of it.
So
Dusted off. I've seen a graph where public respect for politicians, doctors, blah blah blah. It's all going down except for the scientists. It's true.
So there's quite a complex things going on. We also, there's a whole range of things going on. But I don't think we live in a society that's innately fearful of science, although we often think that that's the case. And I think that does a disservice to actually what's really going on in some of these cases.
It might be so fearful that you mess with us.
This question's for Lawrence. I was looking at the Australia website and they said that it can't obtain a patent for a synthesized DNA sequence if it replicates anything in a human or other organism. But you can if it's completely novel. So how do those patent laws affect funding and the direction of your research? Is there a push to projects which involve the synthesis of completely novel sequences and use of those in your systems, or do you have pretty much free choice?
So personally, it doesn't affect me so much because I'm not doing anything for intellectual property. But I would imagine that if you're a scientist and you're trying to develop a product which you wanted to get an IP on, then potentially that would be a problem. The other reason why it's not so much a problem for me is that there are so many possible combinations of DNA sequence that for my purposes, when I'm using it not for an information carrier but to construct something, I can normally come up with another sequence which doesn't exist in an organism. But I imagine that's going to be a big issue probably further down the track when people are using DNA nanotechnology to develop new technology and trying to patent. It's possibly a question that might be better answered than I do.
The interesting thing about the synthetic biology community is, of course, that from the start it was a very much open source driven kind of community. And indeed also the database at MIT, etc. So the whole idea was we should keep it open. Problem, of course, is at one point there will be people who want to commercialize with the patent. And then it would be really interesting to see what the tension is between that desire to have patents and the overall attitude that has been an open source kind of attitude.
Well, what makes you say that it started off more open source? Surely from the beginning there were always people thinking about whether or not you can use this.
Yes, but I mean, for example, also this competition and other important events within the field, you could say, are more or less carried by kind of open source commons mentality, at least nowadays.
But I also think that the university conversation around IP is changing, and so after Bob Doyle in the US, the motion for the major US research institutions was protect everything, and that's really changing. So and it's not significant that IGEM is at a major, US research institution, and it has this kind of open access kind of dimension to it. So that there's a lot of conversation there around do we need the same kind of patenting arrangements at a university level that we once assumed we did, because there's a kind of theory there that actually patenting slows down innovation because it locks everything into these kind of arcane kind of arrangements, and a lot folks in the FDA. And the FDA, you know, the kind of pinnacle of an organisation known for being kind of slow and kind of wrapped up in a particular kind of model of kind of proprietary arrangement with companies particularly, is now experimenting with open source regulation. Yeah. This is a kind of new world, and it's a very interesting kind of world to be playing in, but it's certainly the conversation is changing.
I might just take one last question for you.
Yeah, I was wondering a bit about patents actually. So this happens too, right? What if you like design something, right, and then 20 years, like maybe 5 years later, they figure out that this actually is naturally occurring kind of thing. Like this happens quite a bit because you design something, right, and then we always find new organisms like under a rock somewhere else. Because although it has a mechanism that the quality is out, does that mean our patent becomes invalid? And also, there's like in like biology a lot, like if you get a mutation, right, sometimes it'll just make the molecule slightly worse, and then does that count as a different thing overall? Like, will it just bypass the patent because it's worse and it's not identical? It's just does a similar function.
The question is if the process through which you found out that it is worse, if that's an original process or not, then you can patent that process. But if you just find a new bacteria in nature, this bacteria has exactly the same, you know, elements as the one that are produced in the lab. Artificially, you could say, I don't know if that makes any sense, but then your patent is useless, because when you can find it in nature, then it is a natural artifact which you, at the moment at least, cannot patent. You cannot find an animal in the sea and just then bring it to the patent office and say, I'm going to patent this animal. You can't.
Unless it's one of your artificial salmon.
Unless it's one of my artificial cells. But I mean, that's actually a good example, because when those artificial cells jump out of their cage and go into this ocean and start reproducing with all the other salmons, you know, then are these now all artificial cells that all fall under the patent? I mean, this is an exact question, of course, applied to the soybeans, and you know, if it would fly over from one crop to the field from the farmer next door, and you know, then there was a huge problem, like his field got infected, and so he was going to sue Monsanto on that. Very complex matter. But I mean, the simple answer is just when you find the same stuff in nature 5 years on, then the patent becomes invalid.
Well, I suppose we could keep talking for hours. We have talked for hours, but we might wrap it up here. Thank you, Lawrence, Mark, Matt, and Mike, so much for being here tonight.
Can I just say, best of luck to you to the team.